Swayam Prabha. Digital India. Educated India.
Dear all, today I will start some tutorials. So these tutorials will help you to understand all the problems. Like I taught you many designs, how to develop biosensors, how to develop different nanobio devices, and then use them for point of care diagnosis. But when you sit for exam, kind of questions may come how to solve this. You should be trained properly, right? So this class, that's why how to train you for exam, like kind of questions may come, and this tutorial also you may get lots of problems, and you may get some novel concept to think for your future. Like if you go for your higher study, if you go for internship for other institute, you may work on this kind of small projects also. So this kind of all the problems I will show you, and I will give you some training so that you can think independently. Let's come those all the problems. So today mainly I will cover the basic tutorials for this whole course. So let's come one by one all the questions, and during the discussions of the answers of the questions, you also may find out and the new design, and I will also solve again the new design. So it is not only the discussions of the questions and answer, also at the same time I will show you the new problems that you can solve based on the current problems, current situations, and like the COVID situations you are facing, the new issue like how to deal with the COVID. Like recently maybe dengue. So how to develop and why to develop, where to develop. Like it also sometimes specific to the region to region. That also you will get some concept. So you can see here I already made a list of the tutorials that how to modify the electrode surface with gold nanoparticles. So I already taught you how to synthesize the gold nanoparticle, but how to modify the gold nanoparticle on the surface. But now systematically you can understand like question to questions how much you have to write. I already gave you the clear concept. Now let's focus on when you write the exam, how to start, how to complete this problem. So first problems I will solve like this way, and the second one is the describe the signal to background ratio for the electrochemical chemical redox cycling. You already know the ECC redox cycling I taught, and I think you can solve this issue. But if I ask you the design or describe here which one signal, which one background, and how we can minimize the background, those things in this problem, and how much you have to write in the exam, that I will cover. Then what is the basic difference between different techniques? Here I just mentioned chronoamperometry, chronocoulometry. Maybe I will bring again the cyclic voltammetry that I will show you. So then what is the non-specific binding of a biosensor? So you know all non-specific binding. Let's show you the answer. Then how we can eliminate, and what is the non-invasive detections, and why this non-invasive is the better than other invasive approach. Then you can define the different technique. So how much you have to write, how to write good way to get the good marks. So let's come then one by one all the questions. Let's describe these questions first. So here I just asked describe the signal to background ratio in the below electrochemical chemical redox cycling biosensor, and how we can obtain highest signal to background ratio. So this is the question. This kind of questions may come during the exam. So let's solve it. And I don't want like a one page writing, just very concise, I mean very simple way you can express your all the answers like point by point. So first questions here, describe the signal to background ratio in this below electrochemical chemical redox cycling. So if I gave you this kind of diagram, so you already understand, right? So here is the electrochemical reactions, right? Electrochemical, see, and here chemical reaction, right, and here chemical, right. So this is the E, that's why this is E, C and C, right. That's why it is ECC redox cycling. It is very much clear. But signal to background ratio, so you have to find out which is signal and which is the background. See, I already taught you in the class, signal means in the presence of the target. So here target is your PFHRP2, your malaria target, this antigen. So if this antigen present, then only this secondary antibody will bind, right. So this secondary antibody, antibody 2, this will bind once this target comes. So this secondary antibody already conjugated with methylene blue. So your signal is responsible if your methylene blue present. So let's then combine everything, like your signals is then the this full reaction is because of the signal, right. So you have to mention, see, in the first things you just have to remember, in this surface you are releasing the electron. Electron releasing means oxidations, right. Can you remember? This is oxidation because electron is released on the surface. So on your surface ruthenium 2 actually generated because of this redox cycling. Ruthenium 2 actually regenerated. That's why during the cycling, if you use 1 more, 2 more, 3 more cycling, more ruthenium 2 will be generated, right, on the surface. That's why you will get the higher signal. So your starting reagent not then ruthenium 2, your starting reagent is the ruthenium 3, and it's actually reduced to ruthenium 2 that you will oxidize on the surface because of some applications of potential. So you need to apply some potential. How much potential you have to apply? That is the positive, some oxidations potential, right. So suppose you have to apply some oxidations potential plus 0.3 volt you are applying. So you are going to measure some chronocoulometry or chronoamperometry. For that you have to apply some potential. So your starting reagent, that's a ruthenium hexamine RuNH363, right. This one your starting reagent, and your methylene blue that is conjugated with the secondary antibody, right, that plus MB methylene blue OX, this form, right, because this one actually will react with the T-cell. So your T-cell also should be there. So your signal is responsible for this reaction, ruthenium hexamine 3 methylene blue X T-cell, that you have to write which one is responsible for your signal. And background, which one is responsible for the background? That is pretty clear. Just remove the target. You have to remove the target. So your target, if you remove this one, then you will not get the methylene blue. So then remove this one. So you will have ruthenium hexamine 3 and T-cell. So RuNH3 whole 6 3 plus T-cell. So this is your background that you have to mention, just very precisely. No need to write like the one-page sentence. You can write what is the signal, what is the background, and then signal to background S by V. You can easily tell that, and you have to get the, like if it is chronoamperometry or chronocoulometry. Suppose you are measuring chronocoulometry CC. So in the y-axis you are measuring current or charge. So y-axis charge like microcoulomb, and x-axis is the time, right, like suppose second is the unit. So signal and background. So background you may get this much. This is the background. Why you are getting too much low current? Because ruthenium hexamine 3 already oxidized form. T-safe is not reacting very fast on the surface. So on surface T-safe reacting very slow. That's why you will get very low background current. Clear? And your signal will be ruthenium hexamine 3 methylene blue X and T-safe. And always you have to keep in mind, while we are using this kind of redox cycling, you have to incubation you need. you need some incubation time. What is incubation time? How long you are, after mixing all the chemical, how long you are waiting before just signal measurement, how long you are waiting. Suppose after this adding all the reagent, you are waiting 10 minutes. So 10 minutes will be your incubation time to measure the signal and background, and this time you have to keep always constant. So background case, if you take 10-minute incubation, and signal case also you will take the 10-minute incubation, then only you can compare the both data. Otherwise, see, if you incubate more than 10 minutes, but slowly this also reaction can be little faster, because ruthenium hexamen 2 plus can be generated little more, so you cannot compare. So always you have to incubate background and signal same time. Okay, so your background signal is ruthenium 3 methyl X T shape, and maybe you are getting this much signal. So this much current, in this case charge, this much charge you are getting. So suppose background you are getting 10 microamps. So this one is a coulomb, like it is the charge, right? So in this case, so just you have to remember this one will be, you know the unit, right? So in this case the unit will be microcoulomb, and signal, because of ECC redox cycling only, you are enhancing the signal to background ratio. You are developing a ultra sensitive biosensors. So it will be definitely around maybe 10,000 or maybe 1,000, something like this, microcoulomb. So something like this. So then you can divide like signal to background ratio, then how much you are getting, that is your, I mean, amplifications. Amplification, right? And that amplification will guide you how sensitive your biosensor, right? So based on these questions, now see, I am just already combining all your concept here. So describe the signal to background ratio in the below electrochemical chemical ECC reduction biosensor, how you can obtain the highest signal to background ratio. So I already discussed. Now you have to find out these things, like this answer. Now you have to write how you can obtain the highest signal to background ratio. I will prefer, let's try to answer it point by point. Like first, to get the highest signal to background ratio, your background should be very low. So your T shape should react very slow on ITO surface, right? This is one point, because if T shape react very low on the surface, then you will get low background current. So you have to select a potential, because you are applying some potential, right? See, this is chronocoulometry. Here you are applying a fixed potential. So on that potential, this T shape are oxidizing, but it is showing very low. But you may apply like not 0.3, maybe 0.9 volt. At that high potential, T shape can be oxidized. It may cause high background current. So it should react slow. That's why your applied potential should be optimum. Should be optimum. Why I am saying optimum? Because some of the cases, maybe you are applying suppose 0.1 volt or 0.3 volt or 0.9 volt. So 0.9 volt case, you are getting maybe T shape is reacting very, very slow, but your signal also very slow. Then your signal to background ratio will not be that much high. But at the 0.3 volt case, your background is little high, but signal is very high. So then signal to background ratio will be very high, right? Then we will choose the optimum potential is 0.3 volt, not 0.1 volt. But 0.9 volt, why we will not choose? Because in that high potential, your T shape can be readily oxidized. Its reaction will be very, very fast. That's why very high potential I should not choose. So we should choose the optimum potential. Okay. And another things, just you have to remember, that's ruthenium hexamen 3 Ru NH3 whole 6 3 plus. This is also your starting reagent. So this also should react very slow, right? So this is also slow reaction. This also should react slow reaction on ITO. Then your answer will be completed. right, and you will get the full marks. Now, that is the things you have to remember. Let's come the second questions. How to modify an electrode surface with gold nanoparticles? So, how to modify the electrode gold nanoparticles? I taught you two methods. One is chemical method for synthesis of gold nanoparticles, right? And another method is the electrodeposition method. Deposition method. So, you can show both the method for your gold nanoparticle modifications on electrode surface. So, chemical method, what you will say? You will synthesize on a beaker, on a test tube, a gold nanoparticles. So, how you will synthesize? You have to use HAuCl4, a gold salt, right? And you have to use a reducing agent. Suppose sodium borohydride you are using, plus a stabilizer. Why you need a stabilizer? Because it will not make all the nanoparticles together, like not make a coagulation, means so that all the nanoparticles should not come together and make a big particles, right? Not a clump like this. So, they should be well separated or monodispersed. For that, you have to use a stabilizer. For example, sodium citrate. That you can say, like by using this one, I will synthesize the gold nanoparticles. Then I will drop this gold nanoparticle on a amine functionalized surface, right? As I told, amine functionalized surface. So, why we need the amine functionalized surface? Because amine group and gold nanoparticles, they have the strong interaction, they can easily bind the surface. So, because after the modifications of the surface, you have to wash the surface thoroughly with some buffer sample. Buffer means something like PBS, phosphate buffer saline. You have to wash it. So, the non-bound one will wash out from the surface and you will get a reproducible surface every time. Otherwise, if you not wash properly, number of nanoparticles may be not same always. So, you have to be careful about the washings also. And this amine modification of the surface, I think that I already taught you. Maybe I will show you some more questions how to modify the amine surface, how to functionalizations. That I will just give you more example, but that I already taught in the class. So, like this way you can answer one part. You have to first chemically synthesize the gold nanoparticles, then you can draw from the amine functionalized surface. Just keep in mind that you already know that during the class I taught, but no need to write the answer everything on a questions in the answer sheet while I will give you the questions, this kind of question. Before the amine modifications, you have to clean the surface properly, right? You can remember, so that your surface become more hydrophilic, not hydrophobic. That process you have to follow, but that no need to write during your exam, like this way. So, chemical method you can complete. Now, come to the electrodeposition method. Electrodeposition means you have to take a very clean electrode surface, suppose ITO, clean surface, right? Always you have to clean. Otherwise, if there is lots of impurity, and if you deposit your gold nanoparticle on the surface, so they will actually deposit on the impurities. So, the surface will not be that much reproducible, and that is not good for the biosensor development. Okay, always you have to clean properly the surface before depositions any kind of nanomaterial. So, this surface you have to use as a working electrode on a electrode 3 electrode system, right? You know, 3 electrode system electrochemical cell. Electrochemical cell. In the 3 electrode system electrochemical cell, your ITO will behave as a working electrode, and you have to use the electrolyte, right? The electrolyte will be your chloroauric acid, right? HAuCl4, and we will not use very high concentrations of the chloroauric acids. We will use like 0.1 millimolar or maybe 1 millimolar chloroauric acid. Then you can dip your reference electrode and your counter electrode. Okay. So, reference electrode, counter electrode, your working electrode, then add this all three in a potentiostat, right? Potentiostat, and in the potentiostat now we apply, generally we like here to apply negative potential, so that your HACl4, that is 3 oxidation state, it will go to the gold nanoparticle, that is 0 oxidation state. So, you will apply a negative potential. Okay. So, once you apply negative potential, then gold nanoparticle will be deposited here, and you will get gold nanoparticle deposited ITO surface. Clear? Like this way. So, you can modify a electrode with gold nanoparticles. Okay. So, this part done. Now, the second part of the questions. So, in the first part of the question there was 2 parts, right? How to synthesize. One is the chemical process and another is the electrodeposition process. Now, let us come here, like how to immobilize the antibody. See, your surface you have lots of gold nanoparticles. Now, let us immobilize your antibody. So, you can choose a antibody, primary and AV1, with thiolated, means thiol conjugated, thiol conjugated antibody. Why I choose thiol conjugated antibody? Because gold and thiol, they have very strong they very strong interactions. Immediately they can bind. Maybe few minutes is enough. Then thiol, and because of thiol and gold, you will get a very good sensor surface, antibody modified gold surface. And now this surface is ready for detection. So, this surface now ready. So, now specific, suppose you are immobilization malaria antibody, then it can detect malaria. If it is dengue, and dengue means it can detect dengue. If it is any kind of cancer, it can detect the cancer. So, this is the basic concept you can write during the exam. Not everything, but like point by point, 1, 2, 3, like this way. If you can answer, that is really good. But generally, in this NPTEL, I will prefer to give you some MCQ type, so that you can try to, you have to remember this kind of the concept and you have to solve the question. But as this is the tutorial, I am just giving all the concept, and like this way you can think some new idea also. Now, here you can see what is the basic difference between the chronoamperometry and coulometry. I already told you, I have taught many times what is the chronoamperometry, what is the chronocoulometry. Amperometry CA, coulometry CC. So, let us make a basic difference, CA and CC. See, both cases, just try to remember CA like this, right? CC like this. What is the y-axis? Y-axis is the current, x-axis is the time. As I said, without unit it is meaningless. So, always write time second, current is micro, and coulometry, y-axis is the charge, coulomb, microcoulomb, and x-axis is the time second. So, that is the unique difference, that here we are measuring current with respect to time, and CC case we are measuring charge with respect to time. Okay. And see here, chronoamperometry case, like it is at the very beginning, see the current is very high, then it is decrease, then it will slowly, it will be equilibrium. Why it happened like this? Because on the electrode surface, suppose you are, suppose you are oxidizing here, right? This is oxidation based chronoamperometry, right? You are oxidizing. So, at the very beginning, oxidizing means you have the ruthenium 2, right? So, at the beginning, you have many ruthenium 2 on the surface. So, when you apply some potential, immediately you will get the high current, because you have a high concentration ruthenium 2, and then ruthenium 2 will form ruthenium 3. And there will be, after that So at the very near surface, at the beginning, there is lots of ruthenium-2. That's why you are getting a very high current. Now ruthenium-2 concentration decrease because ruthenium-2 converted to ruthenium-3, and that's the current will decrease, and after some time, and maybe within 6 seconds or 10 seconds, there will be equilibrium of the 2 and 3. Then you will get like almost stable. And these things, but in the chronocoulometry case, so you are actually integrating, right? In the chronocoulometry case, you are integrating all the current with respect to the time. So with respect to time, as you are integrating it, so always you will get with time it increase. And another point you just have to mention the similarity of these two topics, that always here you are applying a fixed potential, right? Fixed potential, that you have to keep in mind. Both cases you are applying fixed potential, right? Now the next question is, what is the non-specific binding for biosensor? How you can eliminate the non-specific binding, right? I already taught you the non-specific binding. What before that you should know the what a specific binding. So if you have biosensor and if your target bind with the antibody, then this antigen antibody binding is the specific binding. But non-specific means, suppose this target is not bind here, suppose maybe other side of the electrode surface, your secondary antibody that is already labeled, so it should bind with the antigen with target. But if it bind here on the electrode surface somewhere, then it is a not specific site, right? It is non-specific site. So this is the non-specific binding. So how you can eliminate? The best things is that you can wash. First thing is the washing step. If you wash properly, because this binding is not very strong binding, not strong. So if you wash it properly, it will be washed out. This is the one best way. And second method, BSA, bovine serum albumin, in small protein you can use, so that if you after the primary antibody binding, if you use the BSA on the surface, so that the secondary antibody may not bind on the surface very strongly, during the washing they can easily wash out. So you can add PBS buffer and BSA around, maybe you can try suppose few like 1 gram per liter, something like this. You can make a solutions, and then you can drop the surface on the surface. Like this way you can eliminate the non-specific binding. Now what is the non-invasive detection, and why non-invasive is better than invasive method? Non-invasive means, first you know the invasive method, right? Invasive means you have to prick the finger, collect the blood by needle, very painful method, right? Invasive method. Non-invasive, not invasive means like when you collect the sample, like saliva sample, urine sample, sweat sample, they are non-invasive sample. So non-invasive detection means when you are using like those non-invasive sample, like saliva, urine or sweat sample, they are the non-invasive sample, right? And this method, because it is not painful, and also immediately you can collect, even the layman, they can collect the sample by themselves and they can try this detection easily. So this is very important technique. Non-invasive technique is very important technique, and you can easily develop a biosensor for point of sight applications. Even the people, they can use by themselves. Last questions, define the following techniques with diagram. Cyclic voltammetry, chronoamperometry, these questions may come. So what is the technique? Cyclic voltammetry means just you have to draw your diagram, then you have to say this is the oxidation scan, right? This is the reduction scan, and then you can mention this is oxidation peak potential, this is reduction peak potential, this is oxidation peak current, this one reduction peak current, right? Those everything you have to describe with the cyclic voltammetry, that I already taught you. With the proper diagram you have to mention. And amperometry, that just I told you, right? Amperometry means it is something like this. So in the x-axis it is time, and y-axis is the current, and you have to describe all the parameters that I have already taught you. Like this way you can properly answer the questions. Okay, so that's all for today's tutorial. So next tutorial I will bring the more innovative questions so that you can think something new idea, right? And you can plan accordingly for your future study also. It will be very helpful for you. Thank you. That's all for today's class.